I'm Konstantin Novoselov. I'm a professor of physics and material science. Welcome to my exp. What does it mean to do science, and what does it mean to do discoveries? And most often it's probably creation of a different scientific language. So probably the most famous one is the wave function, right? And so this notion of the entanglement in quantum mechanics, but orbits in the atom, nucleus. There are many different different concepts which only exist because we created a special language for those, and we operate within this language. So a change of paradigm usually is associated with the change in language. Just maybe an example a little bit specific from my own field. Centuries ago, people talked about insulators and metals because they measure how they conduct electricity. Later, you think about the band structure and this concept of the band gap and the Fermi level. These days, we're talking more about the topology of the bands. It doesn't mean that we're thinking about some things wrongly, but we constantly developing better and better language to describe the nature, and that's the way how we enhance our understanding, and that's the way how we create the predictive power for our science. The way we currently do technology, we would never be able to understand the way biological objects operate and the origin of life maybe, and to be able to create the synthetic biological or systems, or those which behave in a quasi-biological level. So we would like to try to learn a little bit more from nature and try to make different parts of our systems more active and being active in their own rights, rather than like the existing current materials which are completely passive. That's what we call the origin of complexity. So functionality which we require from our technologies are associated with certain level of complexity. But the functionalities are usually in the technologies which we have these days are only situated on one level. So you take any functional system, I don't know, any electronic components, any like a microprocessor, or any robotic system, any mechanical system, a car, and you take away one component and it immediately stops functioning. So this complexity, the functionality appears on one single level. Whereas in biological systems, you have this complexity, the functionality distributed across many levels, like biological molecules, like proteins, they have certain functionality, the membranes of the cells themselves, and the organs. So the spread of the functionality allows you to achieve much more complex behavior. And that's what we would like to learn from nature, and we would like to delegate certain functions to the material levels, that our materials will be able to generate energy by themselves, to do certain functions in their own rights, maybe to make some decisions depending on the environment. It's not easy, we're not there yet, but lots of people are working on the functional materials these days. We all watched this movie Terminator 2, and there was this robot made from liquid metal and which was able to change shape and change color, but at the same time so be self-healing. At the same time, got some intelligence, can think, and so on. And in order to achieve this, you really need the complexity, the functionality to arise on many different levels, from the very basic material level to the level of the intelligent system inside it. But at this moment of time, we're not doing this. We don't distribute those functionalities across many different levels. But for me, that question how to do this is associated with the origin of complexity, and you can think about it as origin of life as well. And we are really so far away from giving any decent answer to this. You would think that we understand how our body works, and in the recent years, people are talking about new type of computing, for example, neuromorphic computing, where mimicking the way how our brain works. But in fact, we are so far away from understanding this. So this word neuromorphic is a little bit misleading. I mean, we do work on neuromorphic computers here in this institute, but it's still quite a bit far away from gaining the same level of functionalities and complexities as the biological systems. When we talk about the discovery of graphene, we need to realize that it wasn't just a moment, it was a process, and a very long process. It took us a good year before we got into graphene, a good year working with thin graphitic films, studying their quantum properties. And during that year, we didn't really know much about graphene per se. The only thing which we knew for sure that graphene shouldn't exist, and that's the changes in the perception, which is extremely important these days. That we figure it out that monolayer materials, two-dimensional materials, one-atom thick materials, they do exist and they can be stable, and you can work with it and you can study their properties, and they usually have very unusual quantum mechanical properties. And that's exactly how science works, the discovery works, that you basically create a new paradigm. That's the one paradigm is being changed by another. The paradigm that two-dimensional materials don't exist, that you cannot arrange atoms in a flat crystal, two-dimensional crystals, to the discovery that it is indeed possible and we can work with it. My supervisor at the time, very good colleague and friend, Andrei Geim, who created this idea of Friday evening experiments, where you are allowed to mess around a little bit with different fields which are outside of your mainstream work. And graphene was one of those ideas. So when Andrei asked if we can make a transistor out of graphite, and it was obvious that you need to take a thin layer of graphite and then try to make a transistor out of it. And we tried many different ways, and none of those worked, and we pretty much forgot about it. And then one day we were making samples for our scanning tunneling microscope, and that's the usual way how you clean your sample in those microscopes. You just take Scotch tape and you peel away the top layer of a graphite crystal. Usually we throw that away and you use the freshly cleaved crystal only. But at that time, because we've been thinking about this idea how to make thin graphitic films, we thought, why can't we try and make a very thin layer with this Scotch tape? And indeed, the very first device worked really badly, but still worked. So it was clear that that's the way forward, and we continued for a year before we got our first graphene devices. The most important consequence of graphene discovery was the fact of, we would usually use the term isolation of graphene, that we demonstrated that two-dimensional materials, one of them thick materials, can exist, and they can be stable, and you can make experiments with those. And it's immediately gave a kick for the discovery of many other two-dimensional materials. It turned out that graphene is not alone. There is a whole family of two-dimensional crystals. So that's probably the most important consequence of graphene, that a whole new class of materials became available to scientists. Now, of course, it gave rise to many applications, and these days it's being used in batteries, it's being used in composite materials, in electronics, everywhere. But I still think that the fact that graphene changed our paradigm, that two-dimensional materials can exist, is the most influential consequence of that work. Since AI invoked into our life through Chat GPT, through many other ways, people started to believe that it can revolutionize many other areas of our life. And of course, everyone tried to use AI for the development of new materials as well. I should say that we're only at the beginning of this journey. I'm very positive that it's going to work, and that AI is going to be a very important tool for the discovery of materials, especially of the complex materials, the dynamic materials which can evolve by themselves. We're not there yet, but I still believe that the role of a scientist will be very important, that AI is a tool for us, and it is going to be a very powerful tool, but the role of the scientist, of the researcher, will be still dominant. I think it's very wrong to think that you can plan a discovery, that you can put resources into one point and force a discovery. That's not how science works. So science really works by accumulating broad knowledge in many different areas, and those areas, they strongly cross-pollinate and they strongly influence each other. Science needs to be developed as one rather than into a few individual silos.